So right now we just have a really quick video. I have a few more in the pipeline that I think will be more interesting. Um, I think very much more interesting for a wider audience. But for now, I just want to briefly talk about something sort of um, that I guess doesn't really need to be talked about, but I'm going to do it anyway. So basically, I saw a recent paper, and I usually avoid commenting on any paper unless it's to recreate it. But I wanted to comment on this one to sort of defend, I guess, TensorFlow-Quantum, basically. So there's this paper. I did block out the authors. I mean, it's on arXiv. The title's right there. You can find it. I just didn't, I don't know. I don't know why I blocked them out. I just didn't want to create some sort of uh, tension or like blame the authors, or I'm not trying to do anything, you know, mean or like target anyone here. I'm just sort of trying to explain TensorFlow-Quantum at a high level and why I think this paper misinterprets it. So basically, in this paper, the authors introduce a new framework for classical and quantum machine learning, which is fine. I have no problems with people making frameworks. There's of course, a relevant XKCD about that. If I do that, of course, right here. Oh, that's not it. Oh, it's called standards. Yeah, see, there are. This is, of course, a relevant one where, everyone tries to create the universal standard or universal framework, and it just competes with everyone else. But that's neither here nor there. What I'm really talking about, though, is basically this as a point of comparison uses TensorFlow-Quantum. And I think it misinterprets what TensorFlow-Quantum is and what TensorFlow-Quantum can do. So if I do TensorFlow and just highlight that just for the sake of comparison, one, we can sort of see already what the main point is going to be. You see TensorFlow here is classical machine learning library. TensorFlow-Quantum is quantum machine learning, of course. It's worth noting right off the bat that TensorFlow-Quantum is an add-on to TensorFlow. You cannot do anything in TensorFlow-Quantum without TensorFlow. Like TensorFlow is always in TensorFlow-Quantum. It's not only literally in the name, but like in the code. Everything is TensorFlow in TensorFlow-Quantum. Even if you do purely quantum things, they're all tensors. They're all TensorFlow tensors. And so there's that intimate connection there between the two because TensorFlow-Quantum is an add-on, right? Why would you make, and as you can see with PennyLane, for example, PennyLane's not going to reinvent the wheel when it comes to machine learning. There's a billion frameworks out there. You like TensorFlow, PyTorch, JAX, the lesser, whatever, Theano, Cafe, whatever. I don't even know if those still exist. You can use all of those, or at least the first three I said, with PennyLane, because PennyLane doesn't need to do machine learning. That already exists. But TensorFlow-Quantum does both in the sense that TensorFlow-Quantum is part of the broader TensorFlow ecosystem. So anyway, as we can see, if I scroll down, first I want to say this is a nice representation. There's a picture here, classical data, the VQNet models, there's the classical quantum layers differentiators, the execution engine, classical computer, QPU, quantum simulator. Just, for no reason, just as an example, there's a nice figure here as well, the TensorFlow Keras model, which takes classical data or quantum data, TensorFlow layers, TFQ layers, TFQ differentiators, layers, differentiators, DPU, GPU, CPU, QPU, all of this. So what I'm saying is that the framework they're outlining is very similar to what TensorFlow-Quantum already does. Like this figure is basically the same thing as this figure. What's being described here is just TensorFlow-Quantum at a high level. I'm sure there's differences, but as we can see here, there's a claim that we need to unify classical and quantum. And I think there's a lot of packages, not just, Penny Lane. There's also like Tequila and Yao JL, which is a Julia one, but there's lots of these sort of quantum packages. But TensorFlow-Quantum and Penny Lane, I think both serve in a way that can be claimed as unifying. TensorFlow-Quantum especially because it's like TensorFlow. TensorFlow is classical machine learning. TensorFlow-Quantum would be the unification there. So for example, if we're saying, okay, well, they're different packages, like yes, you do have to install different things, and you can't do quantum without classical, which you might say is kind of annoying. But the point I'm trying to make is that from sort of a design point of view, right? If you put TensorFlow-Quantum in TensorFlow, right? Say you merge them, you would have classical plus quantum machine learning in one package. But that package, that would be like, why would you have that? 99% of your users are never using that function. And there's no reason to not separate it out. And if you think about, oh, I want to put TensorFlow and TensorFlow-Quantum, well, one, you're literally reinventing the wheel. TensorFlow already exists. And two, TensorFlow is already the biggest problem that myself and others have with TensorFlow is that it's so bloated. There's so much stuff in the TensorFlow package and the code base that like you don't want to add more things to it. That's like I'm pretty sure that's 99% of the reason people go to new packages is just because TensorFlow and even PyTorch nowadays is becoming it's just too bloated. And so if anything, making TensorFlow-Quantum separate, it's good because it's not contributing to the bloat of TensorFlow, and you can trim TensorFlow down however much you want and still use TensorFlow-Quantum. So what I'm saying is that TensorFlow-Quantum does unite this, and there is, for example, there's mentions of unifying classical and quantum, hybrid optimization, TensorFlow-Quantum can do, and this is also describing TensorFlow PyTorch. Python is used in TensorFlow PyTorch. C++ object-oriented is very useful. But no one likes writing in C++ because it's not as fun. And so just like normal sort of PyTorch TensorFlow, JAX, everything is written in C++ for fast, and then you just put wrappers for Python. So that's the same here. You can see here that VQNet does not need to import Torch, TensorFlow, or other huge classical machine learning libraries. That's not really necessarily a meaningful suggestion here in the sense that there's non-huge machine learning libraries such as JAX, which is there's nothing in. There's like tiny JAX as like an autodiff framework is very small. Like it embraces sort of the slimness of software design because OptAX, which is the optimization, Haiku, Flax, Equinox, whatever, all those neural network libraries are entirely separate from the core of JAX. And JAX is fully integrated or mostly integrated with Penny Lane. And so what's the problem here is that, okay, you don't have to import the whole thing, but the reason with Torch, I agree TensorFlow is bloated, but I think there are non-bloated machine learning libraries that can be used with quantum machine learning. They're big for a reason. There's a lot of stuff in the classical machine learning world. It comes with a complete neural network library. I mean, that's literally reinventing the wheel, assuming it's not doing anything different in the neural network world, like that you just copy. Like I could make it where you don't have to import TensorFlow if I just copy and paste the core of TensorFlow, but that's not really that beneficial as opposed to just using some lighter library or something like that. Classical and quantum machine learning optimizer loss functions all in TensorFlow-Quantum. And the deployment of classical computers and quantum computers is unified compared with frameworks such as TensorFlow-Quantum. It can deploy classical models on quantum computers and deploy quantum models on QPUs. I will note that TensorFlow-Quantum can do this pretty well, actually. I don't know how well it works for like, it works well with Circ and like Google QPU. I don't know how well it works in general. I know there's people working on, I saw there's a PR regarding usage of IBM systems and IonQ systems. So I know people have been running it on those hardwares as well. But the science paper, the science cover paper, that was on quantum machine learning not that long ago. I believe Robert Wong, I might be mispronouncing that name, was one of the first authors, if not the first author on that paper. That used TensorFlow-Quantum, I'm pretty sure, and Circ, and it used machine learning, TensorFlow, and it used quantum execution. So that's a perfect example of executing classical machine learnings on normal classical computers and deploying quantum stuff on QPUs. But you can already, if you specify a backend, you can run things on QPUs now. It's easiest to do with Google Circ QPUs. I've never done it, but I know people who have done it, and like, because getting access to Google QPU is kind of a pain. But there's also people back in the dev meetings, I remember people running on IonQ systems, and that's a whole story behind why line qubits are now enabled. But so this is exactly like what TensorFlow-Quantum is made for, is deploying on classical and quantum computers. I don't know why it's said in opposition to this. That's like, okay, most of the time I use TensorFlow-Quantum, I do it on a simulator, but that's most of the time I do anything. So I don't think that's a very apt comparison. We can see if we go down that it's very similar, as you can see, to TensorFlow PyTorch. You can see the module format. It looks almost identical to PyTorch.nn.conv. Like, all of that seems very. There's a Q tensor, which is very reminiscent of tensors. And then what we see here is a very interesting comparison, and that is, I don't know exactly what's going on here. And that is that assuming these packages are equivalent, right, we can see train loss on some. What's the exact problem? Figure 3. I don't know. Okay, yeah, it's just some MNIST data set right here. But what the confusing thing is, and they said for fairness, we train on all the same stuff. We do cross entropy, atoms, same learning rate, and they're all 20 epochs. Let's see, one is weird because they say 20 epochs. Oh, after stopping, I see. What I was going to say is, assuming the implementations are the same, right, and what they're calculating, assuming they're right, like assuming their atom implementation is correct and you're using the same hyperparameters on a simulator, these should be the exact same curves. There's no reason for them to be different because they're computing the exact same values. You're not, like, implementing something differently is not, should not be, different at all in the results. Like PyTorch and TensorFlow should perform the same. This, if you use, it's true, PyTorch and TensorFlow use different default values, for example, an RMS prop. But if you set all of the values the same and you set the random seeds the same, because as we've seen a lot in classical machine learning, random seeds do matter, they should be computing the exact same functions. And so it's very weird to see these graphs as a point of comparison between TensorFlow and saying, oh, it doesn't, you can see TensorFlow over here doing pretty well, and here maybe I'll defend PyTorch, right? PyTorch is this orangish red one, I think. And I'll be defending PyTorch here because this should be the same as TensorFlow. They're doing the same thing in classical machine learning when it comes right down to it. for basic operations. Maybe at higher levels, there's some really weird cases where like doing things are different. But if you call a feed-forward neural network, it's doing the same exact, it should be doing the same exact map moles. The gradient should be the exact same, and everything should be the same. So I don't understand how these curves are different, is really what I'm saying. And even for quantum machine learning, assuming you're running on simulator, everything should still be the same. Assuming you're running on hardware, the differences should only be due to hardware noise on different runs, which you can't really blame on the package. You can only blame on the hardware. And maybe you can say, okay, well, my software is adaptive to hardware noise or something, but then you're doing a different comparison. It's not just apples to apples. You're saying, oh, my package isn't better, but my hardware adaptiveness is better. So you can see here that like if I run ResNet 18 on TensorFlow and PyTorch, like why are these so there's like an order of magnitude, well, not that much I guess, but they're really off. Like these should be computing the same things if you start with it, right? You do a bunch of map moles, the same exact map moles, you take a gradient, any randomness should be deterministic, right, as a point of comparison, because you have you set the random seeds to be the exact same. But assuming you eliminate randomness, which is not really helpful as a point of comparing packages, then this doesn't make sense to me. It also doesn't make sense as an evaluation of whether a package is good or not, because you have ResNet 18 here, TensorFlow loss versus PyTorch loss. Presumably, I don't know how many seeds it's over, there's no plus or minus there, but like the thing that would probably matter between these two is speed rather than accuracy, assuming they're doing the same operations. I assume this accuracy difference is due to random seeds. And so what matters is speed, not accuracy. They should be the same accuracy. And you can see here, this is similar. This might be just due to some random noise. Oh, that's combined with Qiskit. Yeah, so this is just a validation training. This is just due to noise. So you can see that in here, right, this is more comparisons, but only of their performance, which is, it doesn't make sense to me as to say, oh, it's better, right? Look how much better of a loss it achieves in TensorFlow-Quantum. Let's see, one, assuming you're comparing apples to apples, everything should be the exact same up to hardware noise. Right, like atom is the same, parameter shift rules are the same. Like what's different here? The only thing that different packages have over each other, like the only reason you should choose PennyLane or TensorFlow over each other is their speed, their ease of integration into your current workflow, maybe their scalability, their documentation, stuff like that. But they should be doing the same operations. And I know I got sidetracked a little bit there, but really what I'm saying is I don't think the comparisons are very fair for TensorFlow-Quantum. And I think that TensorFlow-Quantum fills a niche that this paper is ascribing empty. And really I saw the paper and I was just like, I mean, it's not a big enough deal to really, it doesn't matter, but I want to sort of clarify what TensorFlow-Quantum is about. And for people thinking about what packages should I use, I don't want people to see this paper and be like, oh, TensorFlow-Quantum is useless, I don't need it here because I want to do something else. I think TensorFlow-Quantum is great and can be useful. Now, TensorFlow-Quantum is far from perfect, and I have plenty of complaints that I can list in another video, but the problems are not those ascribed to in this paper.